The first step towards resolving everything was gathering precise data. And the name most commonly associated with this new data gathering is Tycho Brahe, who in 1580 makes very, very detailed observations of planetary motion with an unprecedented accuracy. And these are very useful. Interestingly, Brahe got the brilliant equipment and the patronage that he needed to make these observations by making a failed attempt to prove that comets and other such unpredictable changes in the sky are in fact terrestrial events, things that happen on Earth not far, like, say, meteors or shooting stars. They're not, but this didn't sit well with current worldviews. The important thing for us is that he made these very, very precise measurements, and some of them he shared with Johann Kepler, who came to work for him as an assistant. And in 1609, after playing with the data, this was very precise data, good enough that you could take into account the angular measurements, including the position of Earth relative to the planets in this heliocentric model that Kepler was pursuing, precise enough that you could use these angular measurements to actually not just make a three-dimensional model with ordering of the planets, but actually predict the ratios of their sizes. In other words, you could tell whether Mars's orbit was 7 times that of Earth or 3 times that of Earth in radius, rather than just that it's larger. And with this precise data, Kepler discovers, much to his surprise, that 3 very, very simple rules describe all of the motions of all of the planets, and these rules are important, so let's go through them. Kepler's first law says that the orbits of planets, the trajectories that planets follow, are not circles, they're not circles upon circles, they're a simple geometric figure. He found this very surprising. They are ellipses. So what is an ellipse? Well, an ellipse is an oval, squash circle type thing, and it's characterized by 2 special points called the foci, the focus in plural, the foci of the ellipse. And an ellipse is a set of all the points in the plane such that the sum of their distances from the 2 foci is the same. So if I take any point on this ellipse, its distance from this point plus its distance from that point are always the same. And if I take these 2 points to be on top of each other, then I'm designing a circle, because then this is just twice the distance from that one point. So if the 2 focal points are on top of each other, then the ellipse is in fact a circle. So this is what an ellipse is, and Kepler's first law says the orbits of all planets are ellipses such that one of the focal points is in fact the sun. What's in the other focal point? Well, the simulation here gives you a hint. The other focus is the empty focus. There's nothing there. It has no physical significance. It's just a point in space. It's not even the same for all the planets. So the empty focus of Mercury's orbit is nowhere near the empty focus of Venus's orbit, but they both share one focal point, and that is where the sun is. So we need to know a little bit about the geometry of an ellipse. So again, an ellipse is characterized, you see as I run here, by the fact that the sum of these 2 distances is always the same, and I've picked some particular size. And we characterize an ellipse by the size of its semi-minor axis, sort of half of the diameter, if you will, of the ellipse, perpendicular, a line through the center, perpendicular to the line between the foci. That's the shorter axis, so that's why it's a minor axis, and this is half of it. And then the semi-major axis, which is the longer radius. If this is a circle, they'd both be the radius. The longer one is the semi-major axis, so that's along the line between the foci. And an ellipse is characterized either by giving these 2 numbers, or alternatively by giving one of them. Typically we give the semi-major axis, and a parameter called eccentricity that measures how different the 2 axes are from each other. So eccentricity 0 is when the 2 foci are on top of each other, and you have a circle, in fact. And eccentricity 1, which this won't allow me to achieve, is a case where the ellipse is so smushed down that it becomes a straight line, and the semi-minor axis vanishes. The eccentricities of the planets you can reproduce. The most eccentric planetary orbit is Mercury's, and it has an eccentricity of about 0.2. The eccentricity of the Earth is closer to 0.02, which means that it's very close to a circle indeed. This is roughly what the Earth's orbit looks like. So this is Kepler's first law. The orbit of any planet is an ellipse, and the Sun is at one of the focal points of that ellipse. The second law states that as a planet, let me again exaggerate the ellipticity of this, as a planet orbits the Sun, Kepler says, it sweeps out, the line between the planet and the Sun sweeps out equal areas in equal times. So this will give us a demonstration. This turns on a sweep for a particular amount of time, and I can start it whenever I want. And the point is that what this means is the areas of all these triangular shapes have to be the same. The implication is that when the planet is near the Sun, it needs to be traveling faster, so the stubby triangles are broad, whereas when the planet is farther from the Sun, it can travel slower because the longer triangles can be kind of narrow. So not only do Kepler's laws tell you the shape of the orbit, but also the relative speed with which the planet goes. It goes fastest when it's nearest the Sun. This point is called perihelion, the point of nearest approach to the Sun, and it's always along the major axis, you can see. And at the other end of the major axis is the point of farthest distance from the Sun, aphelion, which is where the planet moves most slowly. So these are Kepler's first two laws, and let's go back and summarize that. So we said Kepler's first law was that the orbit of every planet is an ellipse, and these ellipses for the actual planets in the solar system are very close to being circles. The second law tells us how a planet moves faster or slower as it orbits the Sun. This is this law of equal areas. The implication is that a planet moves fastest near perihelion and slowest near aphelion when it's far from the Sun. This is not very dramatic for, say, the Earth. For objects that might orbit the Sun in a far more eccentric orbit, which are sometimes very near the Sun and sometimes very far from the Sun, say comets, this effect is much more dramatic. So when we get to more eccentric orbits, which exist in the universe, we will have to consider this aspect of Kepler's second law more seriously. And this is enough to determine all the orbits of the planets. And this leads to agreement with planetary positions to a precision, by now there were precise observations, that neither the Copernican model, as it was stated, nor the Ptolemaic model could achieve. And this is a very simple, very straightforward geometric construction, so Kepler was sure that he was onto something. Now the third law is different in the sense that it does not address the motion of a planet. It's a relation between the orbits of the motions of the different planets. Remember that Kepler by now had enough information to measure the actual size of the semi-major axes of the planets, at least their ratios. So one could decide, let us call the semi-major axis of Earth's ellipse 1 something. We call it 1 astronomical unit. So by convention, the definition of something called an astronomical unit is that the semi-major axis of an ellipse is typically called A. We will often call this R because whenever possible we'll be talking about circles, and for a circle the semi-major axis, as we saw, is the radius. The semi-major axis of Earth's orbit defines a unit of distance called an astronomical unit. And so we can always measure distances in astronomical units and later figure out how many meters are in astronomical units, something that was difficult for Kepler to do, though he had some measurements. We'll talk later about how precisely we know what an AU is. And what Kepler knows is he then knows the semi-major axes for all of the planets in units of an astronomical unit, or at least he knows their ratios. And what he also knows their sidereal periods, because he has the motion down, and because if you want, we can get it from the synodic period using the Copernican calculation, although since things are not circles, you have to be a little more careful. And he notices the following relation. The square of the period for any planet and the cube of the semi-major axis are related by a constant of proportionality. Now, I can always find a number such that p squared is k times a cubed. Just divide p squared by a cubed. The point is that if you divide p squared by a cubed for each of the 5 planets that Kepler knows about, you get the same answer. And this is very important because this is then not a property of the planet, somehow a property of the solar system. There is something that all these planets share, and it's the value of this ratio. There might be something interesting here. And it's worth expressing this in perhaps a different way. So remember that we can write the period of a planet, a planet's orbit. The sidereal period can be related to, let me imagine that we're only doing circular orbits, so R and A are the same thing, and I'll call A R. And so I can write the period, relate the period to the radius of the orbit and the speed, which I'll assume uniform because it's a circle, with which the planet orbits the sun. So the period is simply the circumference of the orbit, 2 pi r, divided by the speed with which the planet moves. So this is my expression for the period, and A is simply r in this case. So Kepler's law becomes, well, I'd have to square this thing, so 4 pi squared r squared over v squared is k times r cubed. And I have some enticing cancellations here. I can cancel r squared and leave just 1 power of r over here. And what I can find is an equation that we might find use for later that says if you know how far from the sun a planet orbits, from this you can figure out its period. From this you can figure out the speed with which it's moving, multiplying by v squared and dividing by kr. I find that v squared is 4 pi squared over kr, a relation to which we will have time to return. And what is the numerical value of k? Well, k is a kind of funny physical constant, the first of its kind, but we'll meet many of them. Remember that a is a length in meters or astronomical units or whatever it is. P is a length of time, so k is some number of perhaps seconds squared per meters cubed. It is a completely different number of hours squared per mile cubed. K is a physical constant which depends on the units you're using. You can always pick your units of distance and time to make k equal to 1 if you so desire. In natural units that we will try to use, seconds and meters, it most certainly is not 1. But the important thing for us is that k, whatever it is the same for all the planets. And that is hinting at some deep underlying physics because it's something that is true for all of them. Setting this aside for a minute, we have other progress. Galileo, about a year after Kepler obtains his laws, gets his hands on the newest technology, a telescope, a spyglass. And we don't know if he's the first to do it, but he was certainly the first to publish this and to become known for it. He used a telescope to look up in the sky. And he finds many, 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 many exciting things when he looks up at the sky with this newfangled invention. The first thing he finds that Venus, the planet Venus, goes through phases, which is not surprising to us. It's a chunk of rock. It's illuminated by the sun. Its angle to the sun changes. So Venus goes through phases, but in particular, the relation between the phases of Venus and its position in the sky show that sometimes Venus is closer to Earth than the sun is, and we get effectively a new Venus just like the new moon works. But on the other hand, unlike the full moon, which happens when the moon is on the other side of Earth from the sun, Venus is never that 12 hours away from the sun in right ascension. Venus is always near the sun, remember. A full Venus happens when Venus is on the other side of the sun from Earth. And what this means is this does not fit in with the precise parameters of the Ptolemaic model, but it fits very nicely into the Keplerian or even the Copernican model. Also, he discovers that Jupiter has satellites. He sees the 4 Galilean moons, or as he, seeking patronage, calls them, the Medicean stars, moving back and forth around the image of Jupiter, and he realizes quickly that what he's seeing is something, a collection of bodies orbiting Jupiter. Well, they're clearly not orbiting the Earth, so this is an important piece of breaking down the cultural objection to the Earth moving. He sees various exciting things. He sees mountains on the moon. He sees sunspots on the sun. He sees some weird structure on Saturn that later Huygens discovers are the rings of Saturn. So Galileo finds many things with his telescope, and in particular, the evidence of the phases of Venus is really the smoking gun that dooms the geocentric picture, or the Ptolemaic geocentric picture, as we will talk about later. Whether you think that the Earth is stationary and the whole universe is doing a complicated motion or something else, at the end of the day, that's a very difficult and almost philosophical question. We'll see what we can have to say about why we prefer one description over the other, but in particular the fact that Venus is sometimes behind the sun and sometimes in front of the sun, that's now a fact. And this does not fit with the Ptolemaic model. Galileo also applied himself to beginnings of the science of mechanics, the study of motion, and is well known for formulating what is called the principle of inertia. As he put it, an object will retain its state of motion unless disturbed externally. Now, we are all familiar with this in the following painful sense. If you have a refrigerator that's not moving, and you want to set it in motion, you want to change its state of motion from rest to motion, you have to expend quite a bit of effort to move that refrigerator. What Galileo reminds us is, but then if you let it go, the refrigerator will stop. What Galileo realized is that this is an artifact of rubbing against the floor. And if you put the refrigerator on ice or on roller skates and started it moving, it would be just as hard to stop it or change its direction of motion as it was to get it started in the first place. And that is an abstraction that is cannot be understated. Galileo made many brilliant deductions, but he never really got mechanics right. What was missing for Galileo, among many things, but the technical ingredient that was missing was that the mathematics required to discuss mechanics correctly hadn't been invented yet. Real progress awaited Isaac Newton, and Newton also didn't find the right mathematics. It hadn't been invented yet, so Newton just went ahead and invented it. That was the calculus, and we will have to work around it because we don't use calculus. So we've made incredible progress. Look, the planets have, and in general, the heavens have been removed from some spiritual realm of spheres, and we now have objects that are a given distance and a given position in the universe. It's a 3D world out there. There are moons that orbit the planets. This is all a physical system. We can study it. We can observe it. Galileo observes the moon as a moon, something to be observed, not some heavenly object. We have Kepler's laws, and the predictions of Kepler's laws from such simplicity, such precision, is extremely compelling. Moreover, it turns out that these laws are a lot more universal than Kepler could have imagined. In fact, they govern any kind of orbiting system. They govern the solar system. They govern the various moons of Jupiter, as was discovered not long after he published his book. They govern every orbiting system, in some sense, electrons in an atom. Each system is characterized perhaps by a different Kepler constant K. That was a property of our solar system. But the relation, the fact that the orbits are ellipses, and the central object is at one of the focal points, and that the semi-major axes and the periods are related by p squared equals a constant times a cubed for different electrons orbiting a nucleus or different moons orbiting the same planet. This, it turns out, goes way beyond what Kepler put into his model, comes out of it. And in physics, when something is that universal, it tells you that there's some fundamental law underlying it. There's a reason why all of these things share a behavior. And again, these underlying physical laws, of which Kepler was just finding the manifestation in the solar system, were waiting discovery by Newton. So we're now ready to discuss Sir Isaac.